Hello, this is Akshay with another video here, and this video is going to focus on the most important concepts of electricity called heating effect of electric current. So we will see in this video that is how the current can generate heat when it travels through a conductor. But remember that is heat is gonna be generated or can be felt easily when the current flows through high resistance wire. Let us see. Let us have a look of this very, you can say, a concept here. So remember that is we have learnt in our previous discussions that is the role of the resistance of a conductor is to oppose the flow of electric charge or flow or to oppose the motion of electric current. That's what by nature resistance of a conductor does. So when the current flows through a high resistance wire, that's what mark my word high resistance wire. Means the resistance must be on the higher side. Because of the reason that if the resistance is low, then the heat so formed is of negligible amount that can't be easily felt by us. So in order to see or in order to feel the heat being produced in a given conductor, we need to have a conductor of high resistance. Let us see how that happens. So let us go through this very effect of electric current. So when current flows through high resistance wire like nichrome wire, nichrome is an alloy having very high resistance, especially or predominantly made of nickel and chromium. Predominantly. So when the current flows through high resistance wire, then by nature the resistance will oppose the flow of electric charge or the motion of electric current. What will the electric current do over there? Electric current will have to do the work. Obviously, it has to do the work in order to overcome the resistance of that very conductor. As we do in mechanics, if we want to travel on a given road, we have to use the muscular energy in order to overcome the friction being offered by the ground to our feet. So same is here. For the current to get through the resistance over here, the current has to do work. And in order to do work, energy is required. So it means current will use its electrical energy to overcome the resistance of that very conductor. In doing that, the electrical energy being used by electric current to overcome the resistance of conductor does appear in the form of heat energy. And that heat energy heats up the conductor. And and I have told you in my previous videos there, as far as resistance is concerned, what the friction does in mechanics, resistance does in electricity. In winter season, we are used to just rub our palms. Heat is generated. Our palms go hot. Have you thought why? It happens because of friction. When you rub your palms, if you notice it, then you will see one hand goes up, one hand goes, you can say, in the forward direction, another is coming in the backward direction. Both are in opposition to one another. And what's happening? The friction of one palm is playing a role of opposing force for the motion of another palm. And as a result of this, the mechanical energy of our muscles being used to overcome the friction of another palm. In doing that, the mechanical energy which has been used to overcome the friction of another palm is not being lost. Rather, it got transformed. As it is well mentioned in the law of conservation of energy, that energy neither be created nor be destroyed. Rather, it got converted from one form to another form. So the form is gonna change. The mechanical energy which is used to overcome the friction of another palm got converted into heat energy. As the process goes on, you will see your palm, your hand begin to feel heat. And the source of heat is, that is, yes, the mechanical energy which is being used to overcome the friction got transformed into heat energy. And that heat energy makes your palms hot. Same is here. Only minor alteration we are gonna do is that in place of friction, we are gonna take the resistance. So the current, while flowing through the high resistance wire, does work to overcome that very resistance of the conductor. And in order to do the work, the current has to spend its electric energy. And the electrical energy which is used to overcome the resistance of that very conductor never ever gonna be wasted. Rather, it got converted into another form of energy, that is heat energy. And that heat energy makes the conductor hot. And that's how heating effect of electric current takes birth. And this is what the heating effect of electric current is all about. So the key is the high resistance. If the resistance is low, current needs not to use high amount of electrical energy to overcome the lowest amount of resistance. Very simple. It means lowest amount of electrical energy is being used to overcome the lowest amount of resistance. That means lowest amount of heat is gonna generated in that very conductor, which is not easily gonna be felt. So that's why it is specifically being mentioned that in order to feel or see the heating effect of electric current, you need to have a resistor or a resistance which is very high, or a conductor having higher resistance, so that more the opposition can be put up in the path of electric current, and in the process electric current has to do more work in order to overcome that very high resistance. And the more work needs more energy. It means electrical current or electric current has to spend more electrical energy in order to overcome the high resistance of that very conductor. In doing so, the electrical energy which is used to overcome the resistance of that very conductor got converted into the heat energy, and that heat energy heats up the conductor, and this is known as the heating effect of electric current. Since this effect was given by Joule, and hence it is known as the Joule's heating effect of electric current, which states that when current flows through high resistance wire, then heat is generated which makes the conductor hot, and such an effect of electric current is known as the heating effect of electric current. So in this very discussion up till now, you have learnt what is heating effect of electric current, A, B, and what is the origin of heat being generated over there. Now we are gonna move further just to find out the derivation for heating effect of electric current. Let us begin here. Very simple derivation. The previous knowledge must be in your mind so that you can just sail through this very derivation. Let us go through it. We have got a conductor of resistance R, high resistance wire it is, and it is subjected to a potential difference V here. And you know, when potential difference is applied, automatically current begins to flow through the resistor or through the resistance. So here, what we are gonna say, that is, let W be the work done, because charge has to move from one end to another end. Let W be the work done. Here it is, W be the work done to bring Q charge from one end to another end through resistance R in time t under the action of potential difference V. So what's gonna happen? The current will automatically, current I, because charge is flowing with respect to time, it shows that the current I is flowing through this very resistance. In order to make the current to flow through the resistance wire, work required to be done under the action of potential difference V. So this is where we are gonna start. So let W be the work done. Q is the charge, T is the time taken for charge to move from one end to another end, and for that matter work needs to be done under the action of potential difference. In other words, current I under the action of potential difference is flowing through resistance R. So let us just go one by one, and we begin from here that for the current to flow through the resistance, charge needs to move, and for the charge to move from one end to another end, you need to do the work, that is W. So here we will start, that is work done is equal to, yes, we have learnt in the definition of potential difference, that is potential difference acting across the ends of a conductor is always equal to the work done to bring one unit charge from one end to another end. And if you have got any you can say glimpse or any you can say idea about the potential difference, so let me begin from there. That is what V is equal to W upon Q. That's what the potential difference is all about. Work done to bring one unit charge from one end to another end. So V is equal to W upon Q. Since we know that V is W upon Q, where V is the potential difference, W is the work done, and Q is the electric charge. V is equal to W upon Q. Since work is required to be done in order to make the charge Q to move one end to another end under the action of potential difference V, and that work done, therefore work done W is the product of OB and Q, or W is equal to OB multiplied by Q. That's equation number 1. Now, we know that is Q is the product of I and T. Since I, that is electric current, we have learnt in the definition of electric current that electric current is the rate of flow of charged particle, and mathematically speaking, I is equal to Q upon T. Or we want to have Q here, so Q is equal to IT. So put Q is equal to IT. This is Q. We are going to put IT in equation number 1. We get. Here it is. In place of Q, we are going to put IT. So but the equation 1 is going to be W is equal to V multiplied by IT. That's the equation number 2. Next, that is, yes, this is V, and according to Ohm's law, V is equal to IR. We are going to transform it. V is going to IR by using Ohm's law. V is equal to IR. So put V is equal to IR in equation number 2. We get, so this is equation number 2 here. This is equation number 2, and in place of V, we are gonna put up IR. So equation number 2 becomes W. Therefore, W is equal to, in place of V, it is mentioned IR, and the rest remains the same, that is IT. Or W is equal to I into I square. Here it is, and RT. W is equal to I square RT. Let us suppose that the work done in order to overcome the resistance completely got transformed into heat energy. Means all the work done, whatever the amount of work done you have performed in order to overcome the resistance of that very conductor has got transformed into heat. It means work done is equal to heat energy. But firstly, let me take it as an equation. Let me take it as an equation number third. So here, next, but we are gonna say that whole work got transformed into heat energy. Let us assume that whole work done got transformed into heat energy. So here it is. Work done got transformed, whole work done got transformed into heat energy. Here it is. And therefore, work done is equal to heat energy, or work done, it is W, and heat energy is equal to H. So what is H? H stands for heat energy. So here W is equal to I square RT. So here we will say put W is equal to H in equation number 3rd. Equation number 3rd. But we are gonna have in equation number 3rd, in place of W we will write H, and it's gonna be H. In place of W it is H, and it's equal to I square RT. Yes, that's important. H is equal to I square RT, and this is H is the heat energy being produced, and it is equal to the product of square of current flowing through the conductor. R is the resistance of that very conductor, and the time for which the current flowing through that very conductor. H is equal to I square RT. It's known as the Joule's heating effect. So H is equal to I square RT. That's the, you can say, that is the one part of the conclusion. Okay, what does this mean? No, that's the derivation here. We are gonna go further to just have another, you can say, that is forms of this very heating effect of electric current, Joule's heating effect of electric current. So let me take you to that very stage, but firstly let me just make a few conclusions over here. Since yes, this is what we have got, heating effect of electric current, and that's the derivation for heating effect of electric current. H is equal to I square RT. What does it means? This means number one conclusion, since H is directly proportional to I square, it means heat produced in a conductor is directly proportional to the square of electric current flowing through that very conductor. It means if you are making the current in double, or if you are just the amount of current flowing through the conductor is going to be double, then the heat production is going to be 4 times. Why? 2 square is equal to 4. 4 times, a direct jump. A 4 times heat production gonna be if current is gonna be doubled. So H is directly proportional to I square. Number 2 conclusion is that H is directly proportional to R, double the resistance, double the heat production. Direct relationship going on here. Okay, and third one is H is directly proportional to the time. That is the time T for which the current flows through a conductor. If the current flows for a longer period of time, the heat production obviously gonna be more. So that's because these are the direct relationships here standing between heat production and the current heat production, and resistance, heat production, and time. So that's the 1, 2, 3. 3 conclusions we have drawn out of this very heating effect of electric current, or the Joule's law of heating effect of electric current. This is called Joule's law of heating effect of electric current. Okay, now we are gonna just reach the final stages here. Just gonna do a minor alterations here by using the previous knowledge we have already got. Let us start from here. Ohm's law, you can say that is, this is a triangular technique for Ohm's law. V, and it is I, and it is R. So firstly we are gonna just change I here. Let it be equation number 5. It's gonna be fourth one. Equation number 4, and yes, put I is equal to V upon R. So these are the things what we are gonna do here. Very much handy in numerical problems, depending upon what kind of a physical quantity the numerical is living with. So you can apply that kind of a formula here. So let us have a look of that very new one formula. That's also gonna be the Joule's law of heating effect. Same derivation here. Just a minor modification is going to happen. I is equal to V upon R, coming from the Ohm's law, and therefore put I is equal to V upon R in equation number 4. We have H is equal to, in place of I, what's gonna be V upon R whole square, and it is RT, or H is equal to, it is V square upon R square, and it is RT. So this R goes, here it is, and therefore H is equal to V square T, and it is R. V square T upon R. So one we have got H is equal to I square RT, and now one we have got H is equal to V square T upon R, and the final one we are gonna take this R, put R is equal to V upon I in equation number 4, same equation number 4, we get H is equal to I square, it remains I square, and in place of R you are gonna write V upon I, and rest remains the same, that is T. So I and one I goes away, therefore H is equal to V, and it is I, one I left here, and it is T. So H is equal to VIT. So it's another one. Third one, H is equal to VIT. And it's another one. This one and this one. So all these are the representation for the Joule's law of heating effect. H is equal to I square RT. This is H is I square RT. H is equal to V square T upon R. You can see here, if you are given voltage and resistance and time, heat can be calculated. Here current is missing. Here current and resistance are there. Here voltage is available, V square T upon R. And once again, if you are not given the resistance and still heat production is being asked for, you can apply this kind of a representation, that is H is equal to VIT. So all these three collectively known as Joule's law of heating effect, or this is the representation for the Joule's law of heating effects. So which is gonna be very much handy in solving the numerical problem. So predominantly, and you can say that is the to top it all, that is heat production in a resistance in a conductor having high resistance is always given by this very formula, H is equal to I square RT, and the different forms for H is equal to I square RT are given below here, which can be kept in mind in order to crack the numerical problems. And that's all about this heating effect of electric current.